What does making a better electric motor depend on? The current, the length of wire, the strength of the magnets? You will have seen the motor effect explained in another video. You may want to have a look at it again. In this video, we explore what factors affect the size of the force on a wire carrying an electric current when it's placed in a magnetic field. Can you think how changing the variables just mentioned might influence the force acting on the wire? Pause the video and try to name a few. Let's see how close you were. The current flowing in the wire, I measured in amps, because it is the current that creates the magnetic field around the wire that interacts with the magnetic field of the magnets. How strong the magnets are. This is related to a quantity called magnetic flux density, B, which is measured in Tesla. The length of the wire, shown in yellow, that is in between the magnetic poles. Let's look at each individually before looking how they relate to each other in an equation. To show which way the current is flowing in diagrams, we use this symbol. We imagine we are looking at the point or end of an arrow to represent a current flowing away from you into the screen. This cross in a circle represents the flights of the arrow going away from you. Let's add the concentric shape of the magnetic field using Maxwell's corkscrew rule. Now increasing the current flowing in the wire. You can see that the magnetic field around the wire will increase if the current also increases. Next, let's try to visualize how the magnetic field between a pair of magnets of different strength might look. Which do you think shows stronger magnets? If you picked this, then well done. This is because there are more lines of force, or a greater magnetic flux density between the poles of the magnets. As we have already mentioned, magnetic flux density is measured in Tesla. A typical weak fridge magnet is about 0.001 Tesla. A powerful superconducting magnet, as used in an MRI scanner, is about 1.5 Tesla. A strong electromagnet is of the order of 2 Teslas. Finally, if there is more wire to experience the motor effect, then it seems reasonable to assume that this will also result in a bigger force. More realistically, if this wire was looped around between the magnets, as in an electric motor, then multiple lengths would be added together. This portion of wire shows the part of the wire that experiences the force. So now we have a link between magnetic flux density, B, current, I, and wire length, L. F equals BIL. That was easy, wasn't it? Here, force on the wire is measured in newtons, magnetic flux density in Tesla, current in amps, and length in meters. You can see from the formula that increasing any one variable will give a larger force. To build a powerful electric motor, you need the strongest magnets with the maximum number of loops of wire with the highest current. Can you see the problems with any of these? For example, higher currents will cause heating in the motor, and if using thinner wire to fit in more turnings of wire, this becomes an even bigger problem. Now let's use the formula. Calculate the force on a single wire when the current is 5 amps, the length of the wire in the magnetic field is 5 centimeters, and the magnetic flux density is 0.01 Tesla. Did you get 0.0025 newtons? Hopefully you remembered to convert 5 centimeters into meters. Now, what would the force be if the wire was looped round 3 times, or even 120 times? Pause the video to work it out. So that's how current, magnets, and length relate to each other in an equation.